In the last lecture, we had talked about the 2-qubit and multi-qubit states in general, and then we had proceeded to just introduce the elements of operators which would act on these states, converting them to different types of states. And we had said that if my input is a single qubit and the output is a single qubit, this operation has to be done by a 2 by 2 matrix or an operator corresponding to a 2 by 2 matrix. And we had also pointed out that there is a NOT gate which even classically is a reversible operation, and obviously the corresponding quantum operation, it will also be reversible. And we had said that the NOT operation is taken care of by what we call as an X gate, and X gate has a matrix representation which is the Pauli sigma X matrix, which is 0, 1, 1, 0. Another one which is popularly known as a phase gate. Now a phase gate, what it does is something interesting. It acting on a state 0, it leaves it as 0. So therefore 0 goes to 0, but when it acts on a state 1, it becomes minus 1. So in other words, it selectively provides a phase to one of the bits. So the corresponding operator is given by what is known as Pauli Z operator. So it is also called Z gate. So NOT gate is pictorially represented as X, and Z gate is pictorially represented as Z. However, in general, I could talk about a phase not which simply makes 1 to minus 1, but it could, for example, give a selective phase. So it could also be 0 is left as 0, but the state 1 goes to e to the power I phi times 1. So the corresponding matrix would be 1, 0, 0 e to the power I phi. Of course, you can immediately see that Z gate corresponds to phi is equal to pi, because cos pi plus I sin pi and cos pi is equal to minus 1. There are a few other phase gates which are important. One of them is known as a T gate, where we take the value phi equal to pi by 4. So the correspondingly this is 1, 0, 0 e to the power I pi by 4. This interestingly is also called a pi by 8 gate. Now the reason for this funny nomenclature is that if you pull out a overall phase of e to the power I pi by 8, then the diagonal elements have only pi by 8 along the diagonals. So both these nomenclatures, T gate and pi by 8 gates, are fairly common. The next thing is, what is possible is to have a rotation in a plane. The rotation in a plane is given by the rotation matrix, which is cos theta minus sin theta cos theta, which is rotating in a plane about the z axis, which is obviously a possible rigid rotation. But one of the most important single qubit gates. Now remember, in classical situation, the only 1 qubit or 1 bit gate that was possible was a NOT gate. But we have already seen that several other possibilities exist in case of quantum operations. Now one of these operations is very popular and is known as a Hadamard gate. Now this is very specific to quantum computing for the simple reason that while in classical computing a 0 can either go to 0 or to 1, and similarly a 1 can go to either 0 or to 1, in a quantum computing there are other possibilities. That is, a state 0 or a state 1 can go to a linear combination of 0 and 1 as well. So here is a situation where the state 0 goes to, remember this state 0 is the corresponds to bit 0 in the computational basis, but it goes to 0 plus 1 by square root of 2, which as you know is the one of the bases in the diagonal basis, and state 1 goes to 0 minus 1 divided by square root of 2. Now this is known as a Hadamard gate, and let me sort of explain pictorially what does Hadamard gate stand for. Now first thing you have to realize is, this is there in the picture, but let's look at it. So the Hadamard gate corresponds to a rotation, first a rotation by 90 degrees about the y-axis, followed by a reflection. But before I explain to you this particular diagram, let us recall our representation on a block sphere. So remember, my north pole was state 0, my south pole was state 1, and this is of course the equator. And we had said that the point where the positive z x-axis meets the equator, that is my 0 plus 1 by root 2, and the opposite point, that is the point at which the negative x-axis meets the equator, is 0 minus 1 by square root of 2. So you notice now remember that this is my y-axis. So what we are saying is this, that the Hadamard gate, which takes 0 to 0 plus 1 by root 2 and 1 to 0 minus 1 by root 2. Now how does it work? So the first thing that you do is this, have a 90 degree rotation about the y-axis. Now you notice what will happen in this picture. If you do a 90 degree rotation, now remember when we talk about a rotation, the rotation is always considered to be along the counterclockwise direction as viewed towards the object from the axis. So therefore, if you did that, did a 90 degree rotation, what will happen in the counterclockwise direction, what will happen is that this 0, so let us look at what is happening now. So come to this picture. So I have this situation here, that there is a 0 here, there is a 1 there, okay, and if I now make a counterclockwise rotation, the 0 has come to this point, the 1 has gone to that point, but you notice the state which is minus, which was here, because you have rotated along the counterclockwise direction, that has now gone to the north pole. But that is not the normal position of the north pole. The 0 and 1 are properly placed, but the minus state should not be on the north pole, but should go to the south pole. So therefore, what you require now is a transformation which inverts this plus and minus while keeping the 0 and 1 the same, which is done by having a reflection about the xy plane, which is what? So therefore, this is the geometrical interpretation of a Hadamard gate. Now, so these are the various single qubit gates. I need a few 2 qubit gates as well. Now, first thing that we realize is this, that all quantum gates may be made to arbitrary degree of precision by only having 1 and 2 qubit gates. And we will see that we require certain other 3 qubit gates for a complete description, but on the other hand, if you just want to have single qubit gates, this is good enough, 1 and 2 qubit gates. Now, so first we talk about some 2 qubit gates. Now, one of the 2 qubits gate, which is also very fundamental in quantum computing, is what is known as a C0 gate. Its full form is actually controlled NOT gate. The controlled NOT gate works like this. Now, suppose this is my input side. I am essentially drawing something which is the direction in which the logic is flowing. So, this is my input side. So, there are 2 qubits on the input side. One is what is known as the control. So, the upper one is control bit, and this is known as a target bit. So, supposing my control is A and target is B. Now, the rule for the controlled NOT gate is that whenever the control bit is 0, nothing happens to the target bit. So, if A is equal to 0, B remains B. But if A is equal to 1, then the B becomes B bar, that is B is flipped, that is 0. If B is 0, it becomes 1, if B is 1, it becomes 0. And the way the C0 gate is represented in a quantum circuit is to have a control there with a small dot there and a symbol for the bit. Now, what about its matrix representation? The matrix representation is shown in the slide. So, look at it. If A is 0, B is 0, the B prime, which is the output, it remains 0 because the control bit is 0. Second case also, control bit is 0, target bit is 1. So, the target bit is unchanged, remains 1. But if A is equal to 1, in these 2 cases, if B is 0, B prime, that is output is 1, if B is 1, output is 0. I can represent this. Remember, I gave you a basis for the 2 qubit, which was 1 0 0 0 0 1 0 0, etc. And this basis is written as the following. I have 1 0 0 0. In this basis, the C0 matrix is 0 1 0 0 0 0 0 1 0 0 1 0. So, notice this, that this block is essentially a sigma x matrix, and this can operate on one of the 4 basis states, right. So one of the 4 basis states where the first 2 entries correspond to control and the lower 2 entries correspond to the target, and you can sort of convince yourself. Look at it. For example, what happens when this is 0 0 1 0? What does it mean? So, this means basically my state is 1 0, because this is the representation for 1 0. Now, do the matrix multiplication. Since the control bit is 1, this means I would get the target bit to be equal to 1. Now, you can multiply this, you can see that this gives me 0 0, okay, and 3 zeros, so 0 1, which is just the representation of the bit 1 1, which is what I expect, because the control bit is 1, so therefore the target is flipped. So, this is my C0 gate. Now, remember I talked to you regarding Bell state. Now, with the 2 things that we have just introduced, I can design a computing circuit, quantum circuit, which will give me a Bell state. Now, let us see. look at, for example, the Bell state that I would try to get is given by 0 0 minus 1 1 by root 2. Let's see how it works. And what you can do as an exercise is try to form the 4 Bell states, the remaining 3 Bell states. One of them I am explaining. So what I do is this. I take essentially a C0 gate, and my C0 gate, but before I do that, let me draw it out and then I will explain. Okay. So what I do is this. I fix my control bit, the first line, which is control bit, to be 1. And this 1, I set it to be equal to 0 initially. Now the way this circuit is to be looked into is, this is just the direction in which the logic is flowing. So because in time H is appearing earlier than this, so the first qubit would be subjected to a Hadamard gate. So my control bit becomes like this. So I had 1. Now this 1 is subjected to a Hadamard gate. We had seen by definition of the Hadamard gate, this gives me 0 minus 1 divided by square root of 2. So you notice, this control which is there now is not just a single control, either 0 or 1, but is a linear combination of 0 and 1. Now when this qubit is to become 0, this will leave this 0 the same. So in other words, since my target initially was 0, my net state at this stage is 0 minus 1 by root 2 direct product with 0. So which is just 0 0 minus 1 0 divided by square root of 2. Now when I subject this to a C0 gate, in this case the first qubit is 0, that is control bit is 0, so therefore nothing happens to this 0. So when I pass this through a C0 gate, in the second case my control bit is 1, so my 0 0 remains the same, there is a minus sign already there. In this case the control bit is 1, so therefore the target bit 0 will be flipped, 0 will become 1 divided by square root of 2. Now, so this state that you get here is, see, I can't any longer write down the state here and the state there, because these states, the two states here, have become entangled. These have become entangled because there are no individual identification here, and the output state is now 0 0 minus 1 1. What will make it different is if I make a measurement. If I made a measurement of the first qubit and I get a 0, the second qubit automatically becomes 0. And if I get a 1 for the first qubit, the second qubit collapses to 1. But the concept of measurement I will talk later. But this is the way you can produce one of the 4 Bell states, and I would urge you to try to design simple circuits by which you can find the remaining or design the next 3 Bell states. There is another gate which is a 3 qubit gate. Now this can actually even simulate all classical logic gates. It is not done like that because, as I told you, there is a garbage problem there. But this gate is called a CC0 gate. Control not, also called a Toffoli gate. The logic for Toffoli gate is very simple. It has 3 inputs. Let us call them A, B, C. Now, there is a control, double control in this, and this is my target. Both A and B are controlled. The target bit is flipped, that is 0 becomes 1 and 1 becomes 0, if both A and B, both the control become equal to 1, which means if the product of A and B is equal to 1, then only C will be flipped. Now, look at the way a control bit action on the target bit can be written. Now, recall that we had a normal C0 gate where we said the following: if this is A, this is B, we said this is always left without change. Here also A and B will be left without any change. Here we said if A is equal to 1, then only B will change. The way of writing this is to say B prime is equal to B addition modulo 2 of A. This is the same as an XOR, because you notice if B is 0, B prime takes the same value as A, which means if A is 0, B prime is 0. If A is 1, B prime is 1, even though B was 0, which is what C0 gate did. If A is 1, then if B is equal to 0, okay, I still get B prime is equal to 1, which means B has been flipped. If A is 1, B is 1, this is 1 plus 1 XOR 1, which is equal to 0, okay. So, this is the way it works, because it flips only if the control bit is 1. In this case, I can write exactly the same way, and I will say this is equal to C plus addition modulo 2 with the product of A and B. So that if this product equal to 1, which means if either A is equal to 0 or B is equal to 0, it does not work. But if both A and B are 1, then I am adding 1 to C, which will flip it. You can repeat this using this slide. I gave you that the operator representation of the unitary operator, and you can see that that is what works. Let me talk about 2 more gates. First is a swap gate. Swap, as the name suggests, simply interchanges 2 states. So therefore, the operator US working on psi phi, psi is the first bit, phi is the second qubit, which is same as US acting on direct product of psi with phi, it gives me phi psi. So the corresponding operator expression is this, so that psi becomes, the first line was psi, now the first line becomes phi. There is a swap gate which is called a controlled swap gate, which is very useful in quantum computing, and this is the same idea of a swap. This is, there are 2 pictures there represented either by this notation or by that notation, which says there is a control bit, A going to A prime. Remember, A prime always remains A. Now, this acts between B and C, interchanging B and C, making them like this, if the control bit is equal to 1. Now, I have given you a table by which you get the entire truth table, as it is called, of what happens. For example, if A is equal to 1, means control is equal to 1, okay. B is equal to 0, C is equal to 0, right. Then A prime, of course, will always remain 1. B and C, which were 0, will be interchanged, but it does not matter because they were already 0 each, so therefore it remains 0, 0. But if control bit is 1, and B is 1, C is 0, you notice B prime becomes 0, C becomes equal to 1. So this is also known as a Fredkin gate. In the next lecture, we will be talking about quantum circuits and how does one carry out or represent logic, mathematical logic, using these gates which we have talked about. As I have said, to summarize, we have elementary gates which operate on 1 qubit, 2 qubit, or requires 3 qubits. You do not need any more to work even on n qubit states.